Easy, a plug-and-play educational system, is portable, compact and a complete system for microstrip sensor characterization. Ideal for making basic or complex experiments. The students will be introducing in high-energy physics and particle detectors with hands-on experiments. They will be familiarizing with concepts such minimum ionization particles, charge collection, full depletion and charge sharing in strip detectors, among others concepts. The components of the EASY systems are the control unit and the sensor unit. The control unit is the heart of the system communicating with the sensor unit and the computer software. It contains the data acquisition control, and it is also in charge of processing of the sensor data and trigger inputs. In addition, it contains an adjustable height voltage unit for microstrip sensor bias, with voltage and current display, and includes the laser source. The control unit communicates with computer software via USB. The sensor unit accommodates a P-on-N Silicon Microstrip sensor, the same type of sensor used in Atlas detector at LHC. P-on-N strip detectors consist typically of an around 300 microns thick N-type bulk. On one side, a thin layer segments form strips out of P-type material, whereas the back implant is N+. The abrupt junctions are formed between the strips and the bulk silicon. The depletion zone grows from the strips to the backplane, so that the device can operate partially depleted, and the movement of holes forms the signal. The EASY Silicon Microstrip Sensor is segmented in 128 strips. A minimum ionizing particle that traverses a silicon detector loses energy mainly by ionization. When the ionizing particle passes through a silicon atom in the lattice, this will tend to liberate a loosely bound valence electron, generating an electron-hole pair. The free charge carriers formed by ionization in the silicon will move in the detector field in the depleted part of the detector. This is because the ionization in the depleted region is not recombined and also accelerated by the electric field. While in the non-depleted part, there is not electric field and charge will be reconvened. Therefore, only the charge generated in the depletion part will contribute to the signal. The signal generated in silicon detectors is generally of small amplitude, around 24,000 electrons for full depleted 300 micron sensor, hence amplification and shaping stages are required for its further processing. The readout and amplification of the signal of the detector is done by Beetle chip, developed for CERN LHC experiments. The sensor unit also generates trigger signals, which are useful to indicate the exact time at which a particle crosses the microstrip sensor. One of the possible trigger modes of the EASY system is the diode trigger mode. It consists in discriminating a signal generated by a low-noise silicon diode mounted underneath the microstrip sensor, with a gap of few millimeters. In this exercise we are going to study the charge collected by a silicon microstrip sensor when a minimum ionizing particles goes through it, and triggering the diode behind it. The minimum ionizing particles used are 546 kV electrons irradiated by a strontium-90 source. For the experiment we connect the control unit to the sensor unit through flat cable. The flat cable transmits, amount other, high voltage to bias the microstrip sensor and reference voltages, and collects the signals from Beetle chip. The trigger signal from the diode underneath the microstrip sensor is transmitted via the LEMO cable between the control unit to the sensor unit. After power the control unit, we will measure the leak current of the microstrip sensor for different bias voltage applied to plot the characteristic IV curve of a silicon sensor. A perfect detector shows a small rise in current at the beginning and then a long plateau up to the breakthrough voltage. Some imperfections can cause the current to rise with voltage. The EASY control unit is now ready to be connected to the computer via USB port and start the data acquisition software. This software is a graphical user interface, written in C++. It is able to configure the sensor device, receive the data via USB bus, and store it in a file for further analysis. This software also monitors the data during data acquisition, which allows performed a simplified version of the exercises, or, as in a real experiment, to record the data for a more detailed analysis. Before studying the charge formation in a silicon sensor, the student should be introduced in the concept of pedestal, electronic noise, as well as common noise. The pedestal value of the ADC output is an effective offset. For each channel the pedestal value is the measured ADC counts when there is no signal at the input. In the EASY system, the ADC offset has been set to the mean range of the ADC, around 500 ADC counts, to allow read positive and negative signals. The data acquisition software showed the value of the pedestals for the 128 channels. To extract the signal, the pedestal should be subtracted channel by channel. After pedestal subtraction, the fluctuations are due to electronic non-uniformities of each strip. There are two sources of noise. The common mode shift, resulting for an electronic parasite pickup which is specific of the chip and varies with time, fluctuating event by event. And the electronic noise, defined as the fluctuation channel by channel. The common noise and the mean electronic noise are constantly monitored during the data acquisition. The electronic noise is introduced by the readout electronics affecting the charge measurement. The two main noise sources are the detector capacitances and the leakage currents. We can observe how the electronic noise decreases with the depletion voltage due to a reduction of the detector capacitances. The exact calculation of pedestal and noise from the raw data is illustrated in the exercise book. After the introduction of pedestal and noise, the student is ready to learn about signal formation. We can place the strontium-90 source in the carbon window of the sensor unit and place this window over the sensor. We are now ready to start the data acquisition. The event display window shows the charge collected in each of the 128 strips event by event. After pedestal and noise subtractions, we can obtain the charge. The software applies a simple cluster algorithm to determine the charge deposition for each crossing particles. Only the strip with some signal over noise threshold are considered. The charge collected is the sum of the charge collected by all the channels in a cluster. The integrated signal can be displayed for raw data using a linear or logarithmic scale. The large pick around 0 corresponds to all the channel with not charge deposition, so that only noise is collected. Notice that pedestals have been already subtracted. After noise subtraction and cluster reconstruction, we can see the charge spectrum of a minimum ionizing particle. The charge spectrum has an asymmetric distribution with a long tail. When the ionizing particle passes through a silicon atom in the lattice, this will tend to liberate a loosely bound valence electron, generating an electron-hole pair. Occasionally, the ionizing particle will interact with a more tightly bound electron than the silicon valence electrons, and, as a result, will create an electron with a significant amount of kinetic energy. Due to these rare high-energy events, the energy spectrum of the deposited energy in the silicon detector is a non-symmetric distribution. By downloading the data to a file, one can fit the distribution and obtain the more probable charge that correspond to the pick of a Landau convoluted with a Gaussian distribution. Notices that it differs of the mean charge. Also, by placing the cursor over the curve, we can obtain an approximation value of the pick of the distribution, and assume that is the more probable charge measure in ADC count for a faster analysis. Since only the charge generated in the depletion part of the sensor contributes to the signal, varying bias voltage, the students can observe how the charge spectrum variate proportionally to the deplete area of the sensor. By measure the more probable charge for different depletion voltages, they can obtain the characteristic curve of charge collection as a function of the bias voltage. The plot shows how the charge collected grows with bias voltage till a plateau is reached when the sensor is fully depleted. From the graphic, the depletion voltage can be estimated, defined as the bias voltage applied to reach full depletion. So far, the charge collected has been measured in ADC counts. The system provides a calibration curve by injecting pulses with different amplitudes to the preamplifier of Beetle chip. The calibration curve shows the reconstructed charge in ADC's units as a function of the injected charge and number of electrons. The more likely charge collected in a fully depleted 300 micron sensor for a minimum ionizing particle is 156 ADC counts, corresponding to 23,000 electrons. In a Landau convoluted with a Gaussian distribution, the more probable charge is 0.7 times the mean charge. Therefore, a mean charge collected will be around 32,500 electrons. Considering that an average energy of 3.6 electronvolts is required to produce a single electron-hole pair in silicon, the mean charge deposition of a minimum ionizing particle is 117 kiloelectrovolts. EASY comes with an activity book where you can find this exercise and many others. This book provides a full explanation about EASY, the data acquisition system, and the description of the exercise proposed in this video. For more information about the Educational Alibava System, please contact us. Thank you for joining.